Okay, so we are going to continue studying continuous random variables with another one of them, which is exponential random variable. And this is especially important for us because exponential random variable is a generic random variable which can practically quantify random values, continuous random values in real life very frequently. So we say a continuous random variable is said to be exponentially distributed, or that continuous random variable is an exponential random variable if it has the following probability density function. Now, in this probability density function, as you can see, the PDF value, the density value for negative values is always zero. This means an exponential random variable is a non-negative random variable. So it can only take zero or positive real values. And for non-negative values, the density function is defined in this form, which is lambda times e to the power minus lambda x. So here, obviously, the PDF is a function of x value, and lambda is the parameter of this distribution. And lambda should be chosen as a positive value, okay? And this parameter, lambda, is called the rate parameter, just like in the Poisson random variable, lambda is called the rate parameter. So for positive values of the rate parameter, we get a different exponential random variable every time. And so this is the drawing of the PDF here. As you can see, for negative values, it is 0. And for non-negative values, it has a shape like this. As you can see, when x is equal to 0, we get lambda as a response of the function. And as x increases, because lambda is positive and the power of this number e is negative, it is going to converge to 0 as x increases. So this is a converging function that decays to 0 as x goes to infinity. Okay, so this is a PDF because the area under this curve is always 1. So independent of your choice of lambda, as long as you choose a positive lambda, the area under the curve will always be positive, will always be equal to 1. So let's check it. If we integrate the PDF from 0 to infinity, the integral of such a function will get out as minus e to the power minus lambda x. So you know the integral of e to the power x is again e to the power x. However, the integral of e to the power minus lambda x is going to get this minus lambda in front of the exponentiation. Uh, However, we are going to write it in the denominator. So lambda times minus 1 over lambda times e to the power minus lambda x. So lambda and minus 1 over lambda cancels out, and there will only be remaining a minus sign here. So when you continue to compute this integral by plugging in boundaries, if you plug in infinity value first, you are going to get a 0 value here. And if you plug in 0, so e to the power 0 is going to be 1. So minus 1 is going to be a plus 1. So the area under this function, the PDF, will always be 1. So another important and interesting fact about this probability density function is this. So as you can see, the PDF corresponds to a lambda value at 0, and it decays, it decreases to 0 as x goes to infinity. So let's just say it decreases to lambda over 2. So the function becomes halven, and as you can see, at this point, it becomes lambda over 2. So let's just call this distance x here. Okay, so if you move a little, then the function is going to get to its half size. And if you move further with the same distance as before, then the remaining part is going to get to half of its size. So it is going to become lambda over 4. And if you move again at the same amount, it is going to get half to its size, lambda over x. So there is a constant half-life of this function. So at a constant rate, this function is going to get to its half. And so let's repeat the properties of exponential PDF. And the PDF of exponential random variable is a decaying function, which means it is converging to 0 as x goes to infinity. And lambda is the rate parameter of the exponential distribution. And for different values of lambda, as long as lambda is positive, we get a different exponential random variable. And if we choose lambda to be equal to 1, when the rate parameter is equal to 1, such exponential random variable is called a standard exponential random variable. And an exponential random variable can only get non-negative real values, which means we cannot assign any negative value for an exponential random variable. It can only get 0 or positive values. And let's compute the CDF of the exponential random variable now. And you know, the CDF of a continuous random variable is defined as the probability of that random variable being less than or equal to an arbitrary lowercase x value. And in order to determine this probability, we are going to integrate the PDF probability density function from minus infinity to x actually. However, you know, this function, the PDF, admits only 0 values for negative values. So it is a good idea to calculate the integral just from 0 to x. And if you calculate this integral again, you are going to get a minus e to the power minus lambda t, and plugging in values of 0 and x, respectively, x here and 0 here, you are going to get a 1 minus e to the power minus lambda x. So this means what? The CDF, or the cumulative distribution function, or in other words, the total area under the PDF as you move forward to the right-hand side, is going to converge to 1. As you can see, if you plug in infinity value here, e to the power minus infinity will become 0, and the CDF is going to be an increasing function, continuously increasing function in the positive region here. And it is going to converge to 1. And at 0, obviously, it is going to be 0 because the total area on the left-hand side of the PDF at that point is simply 0. And according to this function, it is going to increase to 1. Okay, this is the CDF, the cumulative distribution function of the exponential distribution. And this is the explicit form of it. So the CDF simply is equal to 0 if x is less than 0. And for non-negative values, it is computed as 1 minus e to the power minus lambda x. So this function gives us such probabilities or random variable to be less than or equal to, or simply less than x, because you know, for continuous random variables, the inequalities, strict inequalities and inequalities, they basically mean the same thing as probability. So let's solve a question about exponential random variable now. Suppose that the length of a phone call in minutes is an exponential random variable with rate parameter lambda equal to 1 over 10. So you see here the exponential random variable measures the duration of a telephone call. So it is basically measuring a time, okay, duration. And practically, exponential random variables are mainly used to model length of time or durations, okay? So we are going to solve a few more questions about it and you are going to understand it better. So it is measuring the length of a phone call, and in minutes, the unit of this time duration is in minutes. And the rate parameter is equal to lambda 1 over 10. Okay. And you know, in Poisson distribution, we also call the lambda rate parameter. So we are going to explain the relationship between exponential and the Poisson random variable later on. If someone arrives immediately ahead of you at a public telephone booth, find the probability that you will have to wait more than 10 minutes. Okay, so just in front of you, just as you get in the queue, somebody else has moved forward and get in the telephone booth. So you need to wait until the telephone call of that person ends. Okay, so what is the probability that you will wait more than 10 minutes? Or in other words, what is the probability that this person's telephone call will be longer than 10 minutes? Okay, and we are going to answer a similar probability, the probability that you will have to wait between 10 and 20 minutes, which means what is the probability that this person's telephone call will be between 10 and 20 minutes? Okay, so the duration of the telephone call of that person is an exponential random variable, as it is described in the question, and the rate parameter lambda is equal to 1 over 10. Okay, so question basically gives away this information. And remember, the question mentions that this random variable is modeling the duration of a telephone call in minutes, and the questions are also called in minutes. Okay, so because of that reason, we do not need to be careful about anything, but there may be some tricks in such questions. The random variable may model the duration in minutes, however, the question may be asked in hours, so we need to be very careful about converting the time units here. Okay, so either we convert the time unit of the random variable to the time unit that is asked in the question, or vice versa. Now, the first part asks the probability of waiting more than 10 minutes. Therefore, we are looking for the probability of x being greater than 10. And that is the integral of the PDF, which is lambda times e to the power minus lambda x, where lambda is 1 over 10. And we are going to integrate the PDF in this region from 10 to infinity. And the result of this integral will be e to the power minus 1. And e to the power minus 1 gives you a 0.3679. So this is the probability of waiting more than 10 minutes. Or you can use directly the cumulative distribution function. So such a probability is called the tail probability because it's not similar to the cumulative probability. Cumulative probabilities always indicate less than or equal to sign. So here we are asking the probability of random variable being greater than 10. And the complement of this event is the random variable being less than or equal to 10. So if we subtract the probability of this event from 1, you are going to get the probability of x being greater than 10. And this probability is basically calculated with the cumulative distribution function. So we can say 1 minus the CDF at 10, which is the CDF, which is computed by using the CDF function 1 minus e to the power minus lambda x, where lambda is 1 over 10 and x is 10. You are going to again see that the result is going to be e to the power minus 1. So if you know the cumulative distribution function, if it has a closed form formula, it is always best to use that, because when you integrate the PDFs, you can get confused. However, if you are given a closed form for the cumulative distribution function already, such probabilities can easily be computed using the CDF. In fact, in the second part of the question, where we are looking for the probability of waiting between 10 and 20 minutes, we are directly going to use the CDF function. So this probability is what? If you subtract the probability of x being less than or equal to 10 from the probability of x being less than or equal to 20, you are going to get this probability. Actually, there is a logical mistake here. We need to write x being less than 10 because in this event, 10 is included, whereas when we are subtracting the probability of x being less than 10, we should not include 10 here. However, it doesn't make any change because for continuous random variables, if you remember, a strict inequality or inequality has the same inequality with the equation sign has the same probability. So it works for continuous random variables this time. However, such a mistake, if it is made for a discrete random variable, it can be dangerous. So we basically subtract the CDF at 20. We subtract the CDF at 10 from the CDF at 20. And the CDF at 20 is again computed by 1 minus e to the power minus lambda x, where lambda is 1 over 10 and x is 20 here. And here x is 10. So this means we are subtracting e to the power minus 2 computed here, because ones will cancel out and there's a minus sign here. We are subtracting e to the power minus 2 from e to the power minus 1. And the result is going to be, by the use of a calculator, it is going to be 0.2326. Okay. So let's solve another question. In a bin, there are 8 batteries, 3 of them being of brand A and 5 of them being of brand B. So in this bin, there are 8 batteries and we have different types of batteries and the quantities are given. Though the brands are different, the batteries are indistinguishable. So what does that mean? If you randomly select a battery from this bin, you don't know which brand of battery you get. Okay? It is known that the lifetime of a brand, brand A battery is uniformly distributed between 30 and 70 hours. So we know that if you by chance choose a battery of brand A, it is going to work between 30 and 70 hours. However, it is going to be uniformly distributed. So you know the continuous uniform distribution from our previous slides. And whereas the hourly lifetime of brand B battery is exponentially distributed with rate parameter lambda being equal to 0.02. So as you can see, the question especially indicates that the hourly lifetime of brand B battery is distributed with exponential distribution with rate parameter lambda being equal to 0.02. So the distribution for brand A battery and the distribution for brand B battery are given in the same time units, which is hours. Okay. So what is the probability for a randomly selected battery from the bin to work for at most 45 hours, it says. So we randomly select a battery and we do not know which brand of battery we have selected. And what is the probability for that to work for at most 45 hours? Okay. Actually, if we do not know the brand of battery that we have selected, we do not know its distribution. But if somebody tells us anything about a partial information about the brand, then we know that type A batteries have a lifetime that is uniformly distributed between 30 and 70 hours, where the lower bound parameter is 30 alpha and the upper bound parameter beta is 70. And if we know that it's a brand B battery, then it is going to be exponentially distributed. The lifetime in hours will be exponentially distributed with rate parameter being equal to 0.02. So if we make these expressions, we basically summarize a large information that is provided by the question. However, the question is asking us this: if we randomly select a battery, the type of which we do not know, the brand of which we do not know, what is the probability that it works at most 45 hours? Okay. So we define another random variable that is x. And x is the hourly working lifetime of the randomly selected battery. And the question is asking the probability of x being less than or equal to 45 hours. So at most, it is going to work for 45 hours. So, and we know that if we know the brand of the batteries, then we know the distribution of x. However, if somebody does not give us this information, the distribution of x is unknown at the moment. So we are going to condition the distribution or the lifetime distribution of the battery on the information on brand. Okay, so we are going to define two events. A is going to be the event of selecting a type A battery from the bin, and A complement is going to be the event of selecting a type B battery. Okay, because I mean, if you do not select a type A battery, it is obvious that you are selecting a type B battery. Therefore, selecting a type B battery can also be defined as the event A complement. So probability of event A is 3 over 8 because there are 3 type A, brand A batteries in this bin. And whereas the probability of the complement event selecting a type B battery is going to have a probability of 5 over 8 because there are 5 type B batteries in the bin. Now we are interested in this probability, the probability of a randomly selected battery to be less than or equal to 45. And we are going to condition this probability on the event of selecting a type A battery or not. So we expand this as we have learned in the conditional probability chapter. We are going to multiply it, the probability of selecting a type A battery. And given that we select a type A battery, the probability of the lifetime being less than or equal to 45, plus the probability of selecting a type B battery. And given that we have selected a type B battery, the probability of the lifetime of the battery to be less than or equal to 45 hours. And if you focus on this conditional probability can directly be expressed as the probability of a type A battery's lifetime to be less than or equal to 45. So this conditional information gives us that X is already distributed with the lifetime distribution of a type A battery. So similar to that, if we are given the information that this is a type B battery, then the distribution of the randomly selected battery will be distributed with exponential distribution, which is the distribution of the lifetime of a type B battery. And here, probability A and probability A complement are already calculated, which we can write here. And for a uniform random variable, this is the CDF at 45, and the CDF function of the cumulative distribution function of a uniform random variable is simply x over alpha divided by beta minus x minus alpha divided by beta minus alpha. And for an exponential random variable, the cumulative distribution function is 1 minus e to the power minus lambda times x. So if we compute the both probabilities and multiply with the respective probabilities and sum up, you are going to get the result of 0.5115. So this is not a very hard question. Basically, combines our information or knowledge about the conditional probabilities with events defined over random variables. So this is nothing new that we have not seen. Okay, this is nothing new. We have already seen such questions in conditional probability chapter, and we are combining it with our new knowledge about the probabilities defined over the events using random variables. So let's compute the expected value of an exponential random variable now. In order to calculate the expected value of an exponential random variable, we need to multiply the probability density function with x and integrate it over the domain of the random variable, where the domain is non-negative values, because at anywhere else the PDF value is simply 0. So we integrate the x times PDF in the non-negative region of real numbers. So you see in this integrand, we have x, and there is also an exponential function. So this function is the product of a polynomial and an exponential function. And in order to solve such integrals, we need to use integration by parts. So you know the integration by parts from the calculus course. So if we have an integral in the form of u times dv, we can compute it as u times v minus the integral of v times du. And here we are going to call u to be x, and dv is going to be the remaining part, lambda times e to the power minus lambda x dx. So then, once you define your u and dv parts, you first compute v by taking the integral of this part, and it is going to be minus e to the power minus lambda x, obviously, and du will simply be dx. And by using this formula, we can rewrite the integral that computes the expected value as u times v, which is x times minus e to the power minus lambda x, as here, and integral v times du, which is minus e to the power minus lambda x dx. However, because there's a minus sign here and minus sign here, the intermediary sign becomes a positive, a plus sign. So let's plug in the values of infinity and 0 here. Now, if you plug in infinity, minus x will go to minus infinity, and e to the power minus lambda x is going to get to 0. However, it is going to go to 0 very fast because this is an exponential function. An exponential function dominates a linear function. Because of that reason, when you plug in infinity values, this part is going to be 0. And if you plug in 0 value, again, this part is going to be 0 and this part is going to be 1. And again, you are going to get a 0, which means from this part of the integral, you are going to get nothing. It is going to be 0 minus 0 simply. So all that remains is this part. So we need to compute the integral of e to the power minus lambda x, and the coefficient in front of the power in an exponential function gets in front of it by taking the multiplication inverse, multiplicative inverse of it. So there is a minus 1 over lambda here, e to the power minus lambda x, and if you plug in these values again, if you first plug in infinity, you are going to get e to the power minus infinity as 0. So it is going to be 0. And if you plug in 0 value, you are going to get a minus 1 over lambda. And there's a minus sign here. And as you can see, the expected value is going to be 1 over lambda. So you see, it is interesting. The rate parameter is equal to lambda. However, the expected value is going to be 1 over lambda. Okay? So in order to compute the variance, we first need to compute expected value of x squared. And in order to compute the expected value of x squared, again, we can apply integration by parts. X squared times the PDF in the domain of 0 to infinity. And again, this time we are going to say that u is x squared and dv is lambda times e to the power minus lambda x here. Okay? And if you make the same operations, if you define du and v by looking at this, you are going to get this form to compute the integral. And in order to compute this form, you first calculate this part. Again, this is going to be 0. And here, there will be a 2 times integral from 0 to infinity x times e to the power minus lambda x. Okay? So you know, x times e to the power minus lambda x integrand. This is very similar to the integrand in the expected value. However, there is a missing lambda value here. Therefore, the result of this integral will be expected value of x over lambda, because the lambda value is missing here. Okay? If there was a lambda value here, then this integral will yield you an expected value. However, because the lambda is missing, the integral will yield you an expected value of x divided by lambda. So it is going to be 1 over lambda square in that sense, because the expected value was already computed as 1 over lambda, and it is going to be 1 over lambda square. And there is a 2 here, therefore the expected value of x squared is going to be 2 over lambda square. However, we have not computed the variance yet. In order to compute the variance, remember, we subtract the square of the expectation from the expected value of x squared, which is going to be 2 over lambda square minus square of 1 over lambda, and it is going to be 1 over lambda square. So as a result, you can see the expected value of an exponential random variable which has the rate parameter lambda is going to be 1 over lambda, and its variance is going to be 1 over lambda square. Okay? Now, if the rate parameter is small, then this means both the expectation and variance is going to be large. And if the rate parameter is large, both expected value and the variance, they are going to be small. So let's solve another question here. The light bulbs in a production lot has lifetimes that follow exponential distribution with mean value of 5,000 hours. Okay, so you see in this time, we see that the lifetime of a light bulb, so the duration that it works perfectly, is exponentially distributed. However, the question does not provide us the rate parameter. It provides us the mean value. So the average lifetime of the light bulbs are 5,000 hours. So if the average lifetime of the light bulbs is 5,000 hours, if we say that x is the random variable that denotes the lifetime of a light bulb, then the expected value of x is going to be 5,000 hours. And because we know x is exponentially distributed, the rate parameter will be the multiplicative inverse of the expected value, because expected value is 1 over lambda. Therefore, lambda must be equal to 0.0002. Okay. Now, check this out. The average lifetime of a light bulb is 5,000 hours per bulb. So for each light bulb, the average lifetime is 5,000 hours. And if you take the multiplicative inverse of this, the unit will become bulb per hour. So this means what? On the average, we are consuming 0.0002 light bulbs per hour. Okay? So the rate of usage of these light bulbs is such that small. Okay? So on the average, at every 5,000 hours, we are consuming a light bulb, which means on the average, at every hour, we are consuming 0.0002 light bulbs. So this is the rate of consumption here. So we consume these light bulbs, and the rate of consumption in hourly units is this. Okay? At every 5,000 hour, on the average, we consume a light bulb, and this means on the average, at every hour, we are consuming 0.0002 light bulbs. Okay, so the relationship between the rate parameter and the expected value must be understood if we write these units here. So the first part of the question is asking which value exceeds the lifetimes of the half of the light bulbs. Okay. Now, the question is not asking a probability. So this is not asking, the question is not a probable statement, okay? It's not asking a probable statement. It is asking a quantity that exceeds the lifetimes of the half of the light bulbs. So what does that mean, okay? So there is a critical value, x1, there is a certain lifetime. And this lifetime exceeds half of the lifetime of the batteries, okay? Which means if you randomly select a battery from this production lot, it should have a 0.5 probability to have a less lifetime than this critical quantity. So this quantity, this value, this lifetime exceeds the lifetime of the half of the light bulbs. So the probability of a randomly selected light bulb to be less than, to have a less than, or to have a lifetime that is less than or equal to x1 is going to be 0.5. So the question is asking basically the critical value and the probability is given. Okay, so it is basically asking in an unordinary way. So unordinary way. So the fashion of the question is a little different than the ones that we have solved so far. And for part B, it says find the lifetime that is exceeded with probability 0.05. Okay. Again, it is asking a certain lifetime, and only 5% of the light bulbs in the production lots will have a lifetime that exceeds the certain lifetime. Okay? So the probability of a randomly selected light bulb to exceed this lifetime is going to be 0.05. So in part B, the unknown value x2 is here, and the probability of a randomly selected light bulb from the bin or from the production lot to be greater than this value will be 0.05. Or in other words, the probability of the lifetime of a randomly selected light bulb to have a lifetime that is less than or equal to that certain value is going to be 0.95 if we use the complement events probability. So we are going to solve this part and this part. However, this time the result is known, the probability is known. However, the input of the CDF values, the cumulative distribution functions, are not known. However, we know the formulation of these functions. These are the cumulative distribution functions. So for the first part, the probability of x being less than or equal to x1, which is the CDF at x1, must be equal to 0.5. So in order to solve this question, we need to find the inverse of the CDF, the inverse of the CDF. If we say the CDF is defined as 1 minus e to the power minus lambda x for exponential random variables, and if this is equal to a certain probability such as 0.5, then we can simply calculate the inverse of it by leaving x value here and taking everything on the other side. And obviously that is done by using the natural logarithm. So first we say that 1 minus p is equal to e to the power minus lambda x. And then we compute the natural logarithm of both sides. And if we divide this natural logarithm to minus lambda, then we are going to get x. So this function is the inverse of the cumulative distribution function of the exponential random variable. So here, x1 value can be computed using this inverse CDF, inverse cumulative distribution function, by plugging in the certain probability value, 0.5. And after plugging them, so be careful, your rate parameter is 0.0002, you get an hourly time unit, which means half of the light bulbs in this production lot will have a lifetime that is less than that, and the remaining half of them will have a lifetime that is greater than that. Okay? Similarly, we are interested in a certain lifetime. For that, 95% of the light bulbs in this production lot will have a less lifetime. So we plug this 0.95 again into this inverse CDF, and we compute 14,978. So this means 95% of the light bulbs in this production lot will have a less lifetime than this, and only 5% of the light bulbs will exceed this lifetime. So basically in this question, we have used the inverse CDF to compute certain quantities that divides our distribution into two sections. So let's see. So this is the probability density function in the question, with rate parameter lambda being equal to 0.0002, as you can see here, because the PDF at 0 equals to the rate parameter, and it converges to 0, and the total area under the PDF will be equal to 1. And the area on the left-hand side of this 3,465 hours is 0.5, and the area on the right-hand side of 14,978 is 0.05. Now, we can also use the cumulative distribution function. Again, this cumulative distribution function belongs to an exponential random variable with rate parameter lambda equal to 0.0002. And the CDF at 3,465 is exactly equal to 0.5. However, in order to compute this quantity, we use the inverse of the CDF. So we have used the probability to compute this. And the CDF at 14,978 is 0.95. And in order to compute this quantity, again, we have used the inverse CDF. So at what value the total area on the left-hand side is 0.95 and the total area on the right-hand side is 0.05. So we have used the inverse of the CDF. So using the inverse of CDF will also be very practical in our future studies. So not every time we are being asked about the probabilities. Sometimes in order to measure situations related with risk, sometimes we need to use the quantities for which a certain probability statement holds, just like in this question. So we have checked for what quantity the probability, the cumulative probability is 0.95, or for what quantity the cumulative probability is 0.5. So such questions are related with risk situations in real life.